Hello everyone. Myself, Rashid. I'm from Bangladesh University of Textiles, and today I'm going to talk about our research on devising a vibration-based fall detection system for textile machinery. First of all, I would like to convey my gratitude to the organizing committee for giving me an opportunity to present in this conference. Now, I would like to introduce you to my co-authors, Iftekhar Arafat from Bangladesh University of Textiles, Masfiqur Rahaman from Bangladesh University of Engineering and Technology, and our supervisor of this research, Tarik Reza and Sheikh Mominul from Bangladesh University of Textiles. Now let's talk about what we're going to discuss today in this presentation. Firstly, we're going to discuss the motivation behind our research and the problem that we tried to solve during our research. Next, we're going to see some existing studies that have also worked on solving the same problem as our research. After that, we're going to see an illustration of our proposed methodology and how we conducted our research process. After that, we're going to see the experimental evaluation of our system in real industrial scenario. Finally, we're going to see the findings of our research that we found. Now, in the textile industry, there are different kinds of textile machinery of weaving, knitting, dyeing, and finishing, and all those sectors. Each of this machinery is consists of different mechanical components which are directly responsible for the production of fabric. Damage or a fault in any of these mechanical components of textile machinery can result in the production of faulty fabric. And faulty fabric causes the stoppage of machines and a loss of production, which finally results in loss of profit for the industry. In this figure, we can see a defective fabric is produced due to different type of machinery fault. Now, in our research, what we tried to do is we tried to use machine vibration to detect the machine fault. Now, the whole concept of vibration-based fault detection systems are that if there is any fault in any kind of machinery, it brings a change into the structural dynamics of the machine. And there is a standard amount of vibration for each machinery. And this standard amount of vibration depends on the structural condition of the machine. So when there is a fault and if there is a change in the structural dynamics, the vibration of the machine should also change due to that. This is the concept that we try to apply in our research. Now, there have been several studies and researches done for machine fault detection. Firstly, we can talk about the vibration-based fault detection systems. The problem of these kind of approaches are that these systems mostly are based on simulation data, not real industrial data set. And those who are of real industrial data set, they can only tell if the machine is faulty. You cannot really specify the type of fault that is found in the machine. So it makes it really difficult to remedy the problem and find the source of the problem in the machine. There have been also approaches of photoelectric-based fault detection, but the problem of these approaches are really difficult to implement in textile machinery, and these are also really expensive. So this makes this kind of system unrealistic for real industrial use. Finally, there is an indirect approach of detection of machine fault, which is fabric defect-based fault detection systems. In this system, firstly, fabric defect is detected, and from the fabric defect, we can determine that the machine, any component of the machine is defective. The problem of these approaches are that fabric have to be already defective for the machine fault to be found. So we cannot really detect the machine fault before any faulty output fabric is produced, which makes this system very difficult to implement and which causes loss of production. Now, in our research, what we did, we created six artificial pulse in textile machinery, and then we measured the vibration during this fault combinations. And the six artificial pulses that we created were created on the core mechanical components of the machine. After that, we conducted fast Fourier analysis on the prepared data set, which tells us about the machine frequency during different faults. We also did statistical analysis on the machine, so on our data set, so that we can extract different statistical features of the data so that we can identify the pattern of change in vibration data during different faults. Finally, we used our data set to train 8 different machine learning algorithms. And after training the models, we use tenfold cross validation to measure the precision, recall, and effort score of our model. Now, you can see an illustration of our methodology. You can see that we installed the ADXL 345 accelerometer on this position of the machine. And we use Arduino Uno Arc3 as our controller module. And then we created 6 artificial pulse and measured the vibration. We stored our data on a laptop or our computer. And after preparing and storing our data set, we firstly conducted fast Fourier analysis, which gives us the machine frequency during different pulse. And we also did statistical analysis to extract different statistical features from our data set. From these two analyses, we actually detected that the vibration does really change during the machine fault. So after determining that, we applied our data set in 8 different machine learning algorithms. We trained the model, and after that, we evaluated our model using tenfold classification. So these are the 6 faults that we created in our machinery. Firstly, there are 3 core components of knitting machine, which is directly responsible for producing knitted fabric. Firstly, there is needle, there is sinker, and there is hem. We conducted our experiment and created the faults in needle and sinkers of knitting machine. Firstly, we pulled out a needle, completely fine needle from the machine, and then started the machine. So it created faulty fabric. Then we broke in a hook of the needle and we installed the defected needle. We broke the latch of the needle and then we installed the latch broken needle in the machine. And during these 3 conditions, we measured the machine vibration for 2 minutes at a 50 sampling rate per second. And in terms of sinker fault, we kind of did the same. We pulled out the completely broken sinker from the machine and then ran the machine to produce effective fabric for 3 minutes. We bent a sinker to make it faulty, and we installed this faulty sinker in the machine. We broke the butt of the sinker, and then we installed this broken sinker on the knitting machine. And during these 3 conditions, we measured the machine vibration for 3 minutes and stored the data. Now we did all of these things on real industrial scenario. We went to Saad Knitwear Limited, which is situated in Ghazipur, Bangladesh. Here you can see we have installed our accelerometer on the knitting machine surface, and we are storing data from our sensor. Now, after storing the data, we conducted fast Fourier analysis. Now, what fast Fourier analysis does is it separates the vibration signal into its own individual frequency components. And as a result, since all the machines were running on the production floor at that time, you can see the actual machine frequency at that time by on that spike. And it also gives us information about the actual machine vibration amplitude. So we do this for all kind of faulty condition data for normal condition and missing needle conditions. And as a result, we can see different graphs of vibration uh, due, and we can compare that later. Now, if we see the comparison of the vibration amplitude and vibration frequency, you can see that the vibration amplitude changes significantly during different pulses, and the vibration frequency also changes during different pulses. Now, firstly, we are talking about the needle pulse. It's the same case in terms of sinker pulse. You can see in the sinker pulse that the vibration amplitude also changes during different pulse, and the vibration sinker also changes during different sinker pulse. So from this to analysis, I can actually say that the vibration does change and vary during the different pulse. Now we had to be more sure about the vibration variances during the permission pulse. So we also conducted the statistical analysis. In our statistical analysis, we extracted different statistical features like mean, mode, conclusive, skewness, standard deviation, and all that. And then we compared these statistical features during different faulty conditions so that we can identify if the vibration changes during different faults. Now, since our accelerometer collects vibration data from three different axes, we compile all of this data into this graph. As you can see that the mean acceleration of three different axes does really vary during different faults. So you can see clear differences in different faults. And in terms of mode acceleration, it's the same case. You can see that in three different axes, the vibration amplitude changes. Now, it is the same case in terms of skewness and kurtosis. In these statistical features, the vibration also, the statistical features also seem different during different faults. And the standard deviation also see the same. We can see the standard deviation of different fault data is completely different. So from those two analyses, first Bhuiyan analysis and statistical analysis, we actually found completely we can sure that there may be a completely different vibration pattern during different machine calls. So we thought, why don't we apply this data set into machine learning algorithms, since machine learning algorithms can learn the vibration pattern during different faults. And using that, it can detect the type of fault occurring in the machine, and so that we can detect the fault in the machine working. Now, here are the 8 algorithms that we use during our machine learning application. Firstly, as an input, we use the acceleration on three different axes, the X, Y, Z axis, and as an output, we use the type of fault that is occurring in the machine. And then we have trained our 8 different algorithms. And after training these algorithms, we evaluated the trained models using tenfold cross validation. Now, what tenfold cross validation does is that it divides the data set into 10 folds and uses one fold to test and the other 9 folds to train them. And it shuffles the test folds over and over again until all 10 folds have been tested. And finally, it gives us an average precision we call an F1 score from this evaluation. Now, as you can see on this table, that the decision tree classifier has the highest amount of precision we call an F1 score. Gradient boosting is the highest precision, but we call an F1 score. And the other algorithms, the random forest classifier and nearest neighbor preference will share, but the other algorithms will go. Nevertheless, the decision tree classifier was extremely good in detecting the type of fault, so this can be used for machine fault detection. Now, as a conclusion, we can actually say that the existing textile machinery fault detection systems can only detect machine fault after the faulty fabric output has been produced. But in terms of our case, we can detect the machine fault even before any kind of faulty fabric output is produced. And we can do that just by using the machine's vibration signal without any digital additional arrangement, just by using a simple accelerometer, we can detect the machine fault before the production of any faulty output. As a result, there will be no loss of production, there will be no machine stoppage, and it will save cost and it will prevent the loss of profit. Now, in the future, we actually plan to develop a more advanced all data set by changing the condition parameters like raw materials, machine speed, or machine voltage, or different condition parameters, so that our system becomes much more applicable for the textile industry. So, thank you everyone for giving me the opportunity to present in this conference and listening to the presentation. And any kind of questions are welcome. You can contact me through this email address. Thank you.